Hey CW Bio, Mr. Kennedy here, and these are your plate tectonic slash structure of the earth notes that kind of go along with chapter 17 of your book. Today we're going to dig deep into the layers of the earth and learn a little bit about plate tectonics. You know, these big giant masses of land that are floating around on the mantle of the earth and maybe crashing into each other. Yeah, plate tectonics. That's what these notes are all about. To begin, we're going to start by looking at the three layers of the earth. Now, we're not going to get super crazy about studying the inner core, the outer core, and the mantle. Most of the attention in this video is going to go to the crust, the place where we live. So you're just going to have to take my word for the fact that, yeah, there is a core and there is a mantle, but as far as plate tectonics is concerned, our focus, laser focus, is going to be the crust. Okay? So what about the crust? As I said a while ago, it is the place where we live. The Earth's crust has two primary components. There's continental crust and oceanic crust. Guess where the oceanic crust is? Come on, guess. You gonna guess? Guess? Are you guessing? Yeah, it's at the bottom of the ocean. Okay? And that means the continental crust is, well, that's where all the continents are. All right. So the continental crust tends to be super thick, especially when compared to the oceanic crust, between 10 and 70 kilometers in thickness. That thick crust is actually pretty lightweight, again, when compared to the oceanic crust. It's buoyant. It floats not only on the mantle, but if it were to come into a head-on collision with the oceanic crust, it would pop up and ride right on top. Okay, continental crust is considered old. Most of it may be forming from things like volcanic eruptions and stuff like that. Oceanic crust is thin. It's about 7 kilometers in depth. So that's only maybe about 3 miles. And it's dense. It's super compact. It's considered young. And it's usually what is formed right after two plates are separating from each other in the ocean, and the magma from the Earth's mantle comes to the surface. That's where we get oceanic crust. Okay. So how do we know what the earth is made out of? How do we know there's an inner core, outer core, mantle, crust, and all this kind of stuff like that? Well, without getting too crazy in the world of geophysics, I'm just going to tell you that geophysical surveys using seismic activity, gravity, magnetics, electrical studies, these things have, basically given us and painted us a picture of what the earth looks like from basically the inside all the way out to the upper levels of the atmosphere. And somebody with way more letters after the end of their last name than I have got the distinct privilege of naming all this stuff. So that's how we, kind of came to the realization that, the earth's kind of like an onion or an ogre. It has layers, right? So there's that inner core, and then there's a layer on top of that. We call that the outer core. And then there's the mantle, which, is another layer. And then you've got, the crust, which is another layer. And then you got all these layers of atmosphere and stuff like that on top. So yeah, the earth is like an onion or an ogre. It has layers. So let's get to this whole plate tectonics thing. What do we want to know about plate tectonics? So when we're talking about plate tectonics, what we're talking about are these plates of crust that are floating around on our mantle. And well, not our mantle, because it's not necessarily mine, but the Earth's mantle. And as they're moving around, maybe they're colliding with one another or slipping past one another or diving underneath another, right? So that's what plate tectonics is all about, studying how the continental and oceanic plates literally interact with each other. And if you look at a map of the world like this one, you could kind of imagine in your mind's eye that there might have been a point at which these continents that we see today maybe would have or could have come together and form kind of like a single landmass. Okay, there are a couple of points in our Earth's history where scientists believe that all of the continents basically came together and then separated. Right, we have this thing called Gondwana land and Pangea, and just different points in the evolution of the planet that scientists think that these, continents had like basically come together and formed like one supercontinent and then maybe gone the other way and broke apart. Okay. What's driving them to do that? Well, there must be something going on in the mantle, right? That these things are floating on that's making it move around. We'll look at that. So the Earth's crust is divided into 12 major plates, and they're moving in a variety of different directions. The plate motion, as I said a while ago, could cause some of like the continents to crash into each other, or plates to crash into each other. Maybe one dives under another, one's floating on top of one, and one's going underneath, or they're slipping side by side. Like all of those interactions are called faults, right? No, it's not your fault that we have faults, but those are faults, okay? So each interaction causes a characteristic set of Earth structures or tectonic features. So, like as you'll see as we keep going here, like if I have one like plate that's diving underneath another one, well, I'm probably going to get like a trench right there where, one plate dives underneath. And then when that plate that's under, the top plate melts, well, maybe I'll get volcanoes or something like that. If I have two plates that just like crash into each other, like maybe I'll get buckling at the surface and I'll get like a mountain range or something. Like that's what I mean by Earth structures or tectonic features, right? So the word tectonic refers to the deformation of the crust as a consequence of plate interaction. So here's our world plates. And you'll notice in this case, like we've got all of the plates kind of like highlighted. It's not separating out like, oh, here's just a continent versus here's an ocean. Like these are the actual plates. Now, I don't have the arrows on here to show what direction these plates are moving, but at the end of the day, like the idea is that these plates are interacting with each other along their edges in a variety of different ways that I described before, like crashing into each other, sliding past, diving underneath, all that good stuff, okay? The plates themselves are rigid, and that rigidity or that rigid surface of the Earth that I referred to a while ago as crust can also be called the lithosphere. The lithosphere is made up of the crust and parts of the upper mantle. And it's that upper mantle that's like literally dragging these plates around, okay? That upper mantle that interacting with these plates is referred to as the asthenosphere, right? So when you think about just below the, crust itself, you've got molten rock, magma, if you will, and that's the asthenosphere. So below the lithosphere, which makes up the tectonic plates, is the asthenosphere, all right? Now, how does the mantle, the asthenosphere, whatever, drag these plates around? Well, you got to look really close at this picture and allow yourself to just kind of imagine that the mantle is, fairly liquid. It's molten rock. And the deeper you go in the mantle, closer to the core, the hotter it's going to get. The closer you get to the surface or the crust, the colder it gets. So this variation in temperature creates what we call a convection cell in the mantle. Convection occurs as like warm things, become less dense and rise. And it's true of air or liquid. So if we have something that's liquid like rock here, because it's super hot, it will actually rise towards the surface where the crust is. And as it gets further away from the core, it starts to cool off. And so as it cools off, it kind of mushrooms out at the surface and then falls back down. So we get these circular moving like currents of molten rock that literally pull and push all of those tectonic plates on the surface in different directions, okay? That's what causes these tectonic features on the surface. So, what happens at these plate boundaries? Well, here's those tectonic features that I mentioned a while ago. If you have two plates that are moving away from each other, we call that a divergent boundary. And the divergent boundary, like the plates move away, and in the middle you'll have like exposed magma that rises to the surface and basically makes a new plate where the two plates separated. Probably the best place to think about where this is happening is along the mid-Atlantic ridge, literally bisecting the country of Iceland. Iceland's a country that's getting bigger, not just because there's volcanoes erupting or whatever like you have in Hawaii, but because literally the two plates that it sits on are moving away from each other, making the island bigger. Like you can go to Iceland and they literally have a bridge that you can walk across, and on one side of the bridge you're on like the North American plate, and on the other side of the bridge you're on the Eurasian plate. And there's this big chasm in the middle. No, it's not like boiling lava, the TV show The Floor is Lava. It's not like that, okay? But that's the idea, right? There's this chasm in the middle, and Iceland is loaded with like volcanic activity and geothermal activity because this separating of these plates brings this magma very close to the surface. And while it sounds scary for Icelanders, realistically, it's proven to be pretty cool because Iceland actually has harnessed this geothermal activity, and literally 100% of their country's energy needs come from water and geothermal power. Like, how cool is that? It's totally self-sustaining. We can't do that someplace like the United States because we don't have that much geothermal activity. One place that I could think of that has a lot is Yellowstone National Park, and that's a national park, so we can't use that as a power plant, right? Convergent boundaries. Convergent boundaries are, as you see there, when plates collide, and there's a couple different ways that convergent boundary can happen. Like you could have two continental plates collide where they literally just the same mass, and they hit each other and then just buckle up. That's what's going on as India is literally crashing into the rest of Asia. If you're a student of history, you might remember a guy who had to take some elephants over the Himalayas. Yeah, so that's the mountain range that is at the northern part of India, and it was caused by India, a piece of continental crust, crashing into Asia. And it's still crashing into Asia at about the same rate your fingernails grow. So I suppose technically the Himalayas could still get taller if it weren't for like erosion and stuff like that, right? Another form of convergent boundary occurs when one plate hits another one that's not the same density, and then it dives underneath. So the light plate stays on top, the heavy one goes underneath, and I have a slide for you on that one in a minute. And the last one's a transform fault. So our plates are going side to side, okay? Best example of this one, the one I want you to think about, good old California San Andreas Fault. It runs all the way up and down our state and basically cuts through the San Francisco Bay Area and then all the way down to like Baja, California. And there we have two plates that are literally slipping like this, okay? So that's a transform fault. And again, you'll see stuff come to the surface from those plates that slip, right? There'll be broken, fragmented pieces of continental crust that'll rise to the surface, but nothing like what you would see if you had the convergent boundary where it just buckles in this great mass of rock and comes to the surface as those plates collide. So this is... in this picture, we've got a couple of things that we can look at here. It's labeled divergent boundary because in the middle of the picture, you can see two plates are moving away from each other. That's a divergent boundary, right? But the other thing I want you to see is what's going on here at the edge. This is that convergent boundary I told you where like one plate rides on top and the other one dives. We call that a subduction zone. That's super cool for us because we actually have one of those along with our transform fault just off the coast of California. If you're a fan of the Central Coast, you're very near a subduction zone. With subduction zones, as you can see, the oceanic plate dives underneath the continental crust. And as it dives underneath and melts, the magma rises to the surface and it finds weak points in that continental crust that were created from that collision. So the crust like fractures and breaks into pieces, and then the magma wiggles its way up through the crust to find the surface, and then we get volcanoes. Now, we don't have a bunch of active volcanoes along the coast of California anymore, but there are remnants. One of my favorite, Morro Rock. If you go to Morro Bay, that rock like that's sitting right there, that's like the inside of an ancient volcano, and it's tied into a volcanic chain of mountains called the Seven Sisters that go from Morro Bay all the way to San Luis Obispo. Don't believe me? Look it up. Go Google Map, right? And check it out from the air, and you'll see mountain, 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 and they're all in a row. Check it out. So this is a subduction zone along the edge. In the middle, at the divergent boundary, that's where they spread. You get a ridge that comes as the magma comes to the surface, and at the edge, that's where they dive, and you get volcanoes, okay? This just kind of shows you some of the pressure and stresses along our oceanic crust. Basically, the most famous, divergent boundary that I can point you to is right here in the Atlantic. This is what's called the Mid-Atlantic Ridge. And right here, literally the oceanic plates in the Atlantic are separating from each other, and you have like this wall of rock that is forming as a result. We don't have one of those in the middle of the Pacific. Like, this is the Pacific plate, and this is as close as we have to a mid-Atlantic ridge here in the Pacific. The thing that's crazy is if you follow this line and you go all the way up here like this, it hits California. There's actually a part of California's coast that is continental crust, and a part that, well, for lack of a better way to put it, isn't, okay? Here's that picture of Iceland that I told you about a little while ago. It's a great example of continental rifting, or basically where you have that country that is straddling two separate tectonic plates. And there's a bridge, like I said, where you can literally walk right across. Tons of volcanic activity as a result. All right, convergent boundaries. So a little more depth and detail here. There are three types of convergent boundaries. I've actually already mentioned all three of them. I don't know if you wrote them down or not, so here's your chance to do so. You have continent-continent collision, continent-oceanic crust collision, and then oceanic-oceanic collision, okay? And basically what you're going to see here is really dependent upon the density of the plates that are colliding. If the density is equal, remember, they hit each other and buckle. If one's heavier than the other, then you get subduction. So this is continent-continent collision. When you get continent-continent, you get a lot of buckling, right? You might get some of, one plate diving under another, but by and large, it's just like crumbling, like a car accident, like two cars like collide and both their hoods like buckle, right? That's what happens, okay? Here's the Himalayas. Told you. Like, India is crashing into like Asia, and that's where we get the Himalayan mountains, okay? This is continent-oceanic crust collision, and so that's where we get the subduction zone, which, again, I already laid out for you along the coast of California. So in subduction, like, you got one heavy plate that dives under a lighter plate, and as that heavier plate like melts, then you get, volcanoes. Good example of this one from this slide that, isn't California is the Andes Mountains in South America. If you like chinchillas, that's where they live, okay? Ocean-ocean plate collision, well, same idea as two continents. When two oceanic plates collides, one's going to run over the other, cause it to sink, right? You're going to get that deformation and then a subduction zone, okay? Best example of ocean-ocean plate collision is the Mariana Trench. It's 11 kilometers deep, right? Like, that's super deep. I think it's like 2.2 mile or 2.2 kilometers to a mile. So that's like 5 miles deep, which a mile is like almost like 5,500 feet. So like that's pushing like 30,000 feet deep. Like, that's deep, okay? That's a lot of water. All right. This is just an example of what you might find in the Marianas Trench. I got to be honest with you, it's so deep. The Marianas Trench, like, we actually know more about the moon than we know about what's going on at the bottom of this trench. We have technology that can get us to the moon and back. We don't have like the technology to take humans to the bottom of the trench and like hang out there for days, okay? Most of what we've done there at the bottom of the trench is using ROVs. This is the transform fault. Okay, so this is a picture of the good old San Andreas Fault in California as the two plates that I mentioned a while ago slip past each other. And from this map, you can get a little bit of an idea of what's going on with what we call not only the Ring of Fire here in the Pacific, but the outlines of all of the other plates that we've been talking about off and on throughout this video. So this Ring of Fire here at the edge of the Pacific plate is called the Ring of Fire because this is a location with a lot of earthquake and volcano activity as a result of the continental plates colliding with the Pacific plate. Okay, so Ring of Fire. All right. Here's another picture of the Ring of Fire so that you can kind of get an idea of just how many volcanoes and earthquakes happen around it. Each of those red dots is a volcano, and with those volcanoes comes subduction zones and earthquakes. So lots and lots and lots of activity along the edge of that Pacific plate. How's that volcano formed? Well, the same way I described it before. You got to have a subduction zone caused by a collision of continental crust with oceanic crust, and then that oceanic crust melts, diving underneath, and then the magma finds its way to the surface through the cracks and crevices, and eventually we get a volcano. Now, there's an exception to that rule in what we call a volcanic hotspot. Hotspots occur, well, basically at random spots where the magma literally eats its way through an oceanic plate. That's how we got Hawaii, right? So there was a magma plume that, like a blowtorch, burned a hole through the bottom of the oceanic plate, and magma came in contact with the ocean, started piling up, and we got an island, right? Over time, that plate has moved, which has resulted in like an island chain. Like you don't just have one big like Hawaiian island. Like you've got an island chain because the oceanic crust keeps moving, and that plume, rising hot plume in the magma keeps burning through, right, new holes and making new islands. I don't know. Maybe one day, like the big island of Hawaii will have like another like sister island right next door. I don't know. We'll see. Now, that brings us to earthquakes. So here again is that picture of the Earth, and it kind of looks like the picture that I showed you a while ago with the whole Ring of Fire thing. Well, you got to remember, if you've got plate tectonics going on that create volcanoes, well, then you're going to have plate tectonics going on that like creates earthquakes too. So pretty much where there's a volcano, there's an earthquake. They kind of go hand in hand, right? So the earthquakes and volcanoes that we experience on this planet are not just randomly distributed wherever, okay? Where did the earthquakes form? Along fault lines, okay? So in a subduction zone or transform fault, that's where you're going to find the most earthquake activity. You're not really going to find a bunch of shaking going on from a divergent boundary because like there's no collision, you know? But if you've got a transform fault, like two plates like grinding against each other, like the San Andreas, like they're going to get stuck, and then pressure builds up and pressure builds up, and the pressure's incredible, and then boom, like they slip, and that's an earthquake. The same thing's true of a subduction zone, right? One plate dives underneath, and then like it's the top of the plate's not like silky smooth, so like it dives underneath and it gets stuck, and then it just folds the other plate, and it's caught, and then one day, boom, it breaks off, and that's where you get your earthquake, okay? So that's what those are all about, okay? So in summary, the Earth's crust, it's made up of 3 layers: core, mantle, crust. On the surface of the Earth, we have tectonic plates, and they move around the globe being pushed around by those convection cells, right? The plates are make up the crust, the upper mantle, and all combined are the lithosphere, and it's the activity in the asthenosphere that basically pushes that lithosphere around, all right? And then volcanoes and earthquakes, like they're closely linked to all this like plate tectonic movement. All right, ladies and gents, I hope you've enjoyed this real quick coverage of plate tectonics, earthquakes, and volcanoes as much as I have. Thanks for digging deep with Earth Science with me. I'm Mr. Kennedy, and I'll see you next time.